By the end of this lesson, you should be able to relate depth to pressure in a liquid, relate density to pressure in a liquid, explain pressure in a liquid and state P equals H rho G. Observe closely the thickness of the wall. Is the thickness of the wall uniform? Why? Look at the strength of the water that gushes out from the dam. What can you say about the water pressure that causes the tremendous energy? Observe the water spurting out from the container, which has identical holes at different heights. Is the water spurting out at the same speed? Is the spurting distance the same for each water jet? Let us look at the cross-section of the container. Points A, B, C, and D are at different depths from the surface of the water. The water jet spurts out fastest and furthest from the lowest hole. What can you say about the pressure in liquid at different depths? The pressure in liquid increases with depth. Why? At point D, the weight of the liquid is the greatest, while point A supports the least weight. Hence, the liquid pressure P at each depth are PD is greater than PC, is greater than PB, is greater than PA. Observe the water spurting out from the container, which has identical holes at the same level. Is the water spurting out at the same speed? Is the spurting distance the same for each water jet? Let us observe further by looking at the cross-section of the container. Look at the jets of water spurting out from the container. What can you say about the liquid pressure at the same level? What happens to this liquid pressure as the water level decreases? The water spurts out at equal speed and distance. Hence, liquid pressure at one depth acts equally in all directions. Liquid pressure decreases as the depth decreases. Similarly, an object in the liquid will experience an equal pressure in all directions. Thus, pressure is a scalar quantity and not a vector quantity because pressure acts in all directions. The setup shown is to determine the relationship between liquid pressure and the density of liquid. Liquid pressure, P, is defined as the height h between the colored water levels in the manometer. Let us carry out an experiment to determine the relationship between liquid pressure and the density of liquid. The manipulated variable is the density of the liquid given in the table as shown. The responding variable is the manometer reading h, and the constant variable is the depth between the mouth of the tinsel funnel and the water surface. The manometer reading for water is given in the table. To find out the manometer reading for methyl alcohol and the glycerin, Just click on the liquids in the measuring cylinder. From the graph of H versus density ρ, the pressure at a particular depth in a liquid is directly proportional to the density of the liquid. Let us now check whether gravitational field strength has any effect on the pressure of the liquid. We know that the Earth has gravitational field strength of 10 Newton per kilogram, while on the Moon the gravitational field strength is 1.67 Newton per kilograms. Liquid pressure, P, is defined as the distance of the water spurted. Let us carry out an experiment to determine the relationship between liquid pressure and the gravitational acceleration. The manipulated variable is the gravitational acceleration as shown. The responding variable is the distance the water spurts, and the constant variable is the depth between the hole and the water surface. Click on the Start button to begin the simulation. From your observation, what can you tell about the relationship between gravitational field strength and pressure? Liquid pressure increases as the gravitational field strength increases. This is due to the greater weight supported at a particular depth on Earth compared to the Moon. The weight supported at a particular depth on the Moon is just 1/6 of the weight supported on Earth. Does surface area affect the pressure in liquids? The U-tube shown consists of two tubes with different surface areas. From the diagram, which point has a greater liquid pressure, point P or point Q? Why? The liquid pressure at P is greater than Q because the left column is higher than the column on the right. Now click on the clip to unscrew it and observe what happens. From your observation, which way did the liquid flow? Why? Does surface area affect the liquid pressure? The liquid flows from higher pressure P to lower pressure Q until the pressure and the levels are the same. The liquid finds its own level. Although the weight of liquid in Q is now greater than P, it acts over a greater area since tube Q is wider. Hence, liquid pressure is independent of surface area. Let us observe further. The liquid poured will reach the same level in each tube. This confirms that pressure at the foot of a liquid column depends only on the vertical depth h of the liquid and not on the tube width or shape. The graphic shows a column of liquid in the form of a cylinder with a depth h. The column of liquid has a base area A and density ρ. From the information given, let us derive the formula for pressure in liquids. Volume of liquid column V equals AH. Mass of liquid column M equals rho V. The force acting on the base of the surface area A is the weight of the column of liquid above it. Weight of liquid column W equals mg equals rho Vg equals rho AHG. Pressure is force per unit area, or pressure equals to weight of liquid column over base area of liquid column. Pressure in liquids P equals rho Hg. The SI unit of pressure is Pascal, which is equivalent to 1 Newton per meter squared. If H is measured in meters, rho in kilogram per meter cube, and G in Newton per kilogram. Hence, the formula for liquid pressure is consistent with the observations from the activities we have done earlier. That is, liquid pressure depends on the density of the liquid, vertical depth, and gravitational field strength.